Good morning, one and all. Sorry for the inconvenience because of some network issues. We delayed with the live session. Good morning, one and all. Once again, we welcome you all for the day 3, session 5 of. Sorry for the inconvenience because of some network issues. We delayed with the live session. Good morning, one and all. Once again, we welcome you all for the day 3, session 5 of. Sorry for the inconvenience because of some network issues. We delayed with the live session.
One second.
Good morning, one and all. Once again, we welcome you all for the day 3, session 5 of the second week AICTE sponsored short-term training program under AQIS Program A on compressive sensing techniques for 5G cellular networks using MATLAB from 22nd to 27th July 2020, organized by Department of Electronics and Communication Engineering, Sri Venkateshwara College of Engineering, Bengaluru, Karnataka. For day 2, we had keynote speakers for morning session, Dr. Dilip Reddy Bolla, Associate Professor, Department of E&CE, SVCE, on the topic Compressive Sensing in 5G, Open Research Opportunities. And for afternoon session, Professor Rajendra Prasad, Assistant Professor, Department of E&CE, SVCE, on topic 5G Development with MATLAB. These were very informative sessions. We would like to thank once again Dr. Dilip Reddy Bolla and Professor Rajendra Prasad from the organizing committee for accepting our invitation and gracing this event. Today's morning session 5 will be delivered by our keynote speaker, Dr. Poornima G R, Professor, SVCE, Bengaluru, on compressive sensing for future communication networks. On behalf of management, principal, and head of the Department of Electronics and Communication Engineering, we welcome you, ma'am, for this event. Let me introduce our speaker to the participants with the brief profile. Dr. Poornima G R is currently working as professor in the Electronics and Communication Engineering Department at Sri Venkateshwara College of Engineering, Bengaluru. Madam obtained PhD degree from Vishveshwaraya Technological University, Belagavi, Karnataka in the year 2019. Completed masters in 2001. Madam had total of 21 years of teaching experience and research and development and focus on development of new algorithms and novel architectures for the MPEG-4 Part 10 decoders. The entire video decoder designs and implementations done in Verilog VLSI embedded system development for ASCIIs. Madam has some research contribution including International Journals 15 and IEEE International Conference in 17 papers and in national conferences and all 4 papers. And ma'am received more than 2.5 crores grants from various prestigious organizations like DST, KSST, and from industries for consulting for industrial projects. Ma'am published 2 patents on meter-to-meter animal intruder and fire detection intimation system for villages surrounding by the forest and grill doors alignment to the train compartments doors on the railway platform. Madam played a vital as coordinator, session chair, keynote speaker for various IEEE sponsored international conferences and workshops and seminars. Madam also published 3 books related to the academia. We are greatly honored and privileged to have you with us for this elite event. With this introduction, I once again welcome and request Madam to take over the session.
Very good morning, Sarla Madam.
Yeah.
Thank you for the nice introduction.
Firstly, I will take this opportunity to thank our management, our principal sir, our head of the department, Dr. Shivshankar sir, and all my team for giving me an opportunity to uh, uh, contribute my talk in the field of compressive sensing techniques for 5G cellular networks. Okay, thank you. So I'll take up my session. Yeah, madam, is it visible?
Yeah, ma'am, it is visible.
Yeah.
Yeah,
Thank
ma'am.
you.
Yeah,
I
ma'am. Thank
welcome wholeheartedly all the participants, the little bit knowledge which I have gained through the various review references which from the conference papers which I have taken. I would like to talk on those. So myself, Poornima. So as we know, I'll be talking the compressing sensing for communication networks. My topic towards the communication networks, but these communication networks, how they have given the scope for all the researchers in the compressive sensing technology. So that is what I'll be speaking. So let me first acknowledge the Cisco annual report, which is published March 9th, 2020, which has given in internet IP traffic approximations and the analysis from the year 2018 to 2023. Based on that, first I'll be discussing why we are moving towards the fifth generation communication networks. What are the research scopes in that? So this report, first let us discuss few important key aspects from this particular report. The Cisco annual internet report says that the global IP traffic, which is going to increase almost three times for the next 5 years. In this, the 26% of IP traffic will grow at a compound annual growth rate from 2017 to 2022. From this aspect, this particular analysis, the Cisco, which has been made not only from the customers, they have gone for the analysis and through the various entrepreneurs, then the users, and then the customers, subscribers. Based on all these feedbacks, they have gone up. They have come up with the this particular report. So from this IP traffic, 26% of the IP traffic, since it is drastically growing from 2017 to 2022, the monthly IP traffic, which is when it is considered, it will reach 50 bytes per capita by 2023. So that is an approximation which has been made from 2017. From in 2017, there were only 16 gigabytes per capita, which was used as an IP traffic. But for the future 2023, it will go per capita as 50 gigabytes. This analysis, it is based on the digital transformation which has been taken surveyed across various business sectors, which includes enterprise, small to medium business, public sectors, and service providers. So this report actually covered the various internet traffic service providers, which includes fixed broadband, wireless Wi-Fi, and mobile communication, mobile networking, which includes 3G, 4G, 5G 5G networking. So this report vertically, which has been approximated the quantitative projections in 4 different fields. The first quantitative projection by Cisco report, it is towards the internet users. The second one, it is based on the number of devices and the device connections through the internet to increase to made that approximation for the internet traffic. The third aspect or the projection they have considered is the network performance. And based on all these surveyed reports, they have concluded with new application requirements will be in the 5G, to which are the domains and what are the requirements, how the architectures have to be built. So these are the quantitative projections which have been derived from the Cisco report. When the internet users have been considered, the number of internet users presently, it is almost one third of the global population. It is one third of the global population is accessing internet access. So this is by 2023, it is going to increase the global population for the internet users as 66%. This drastic growing in the internet users has been summed up from 2018. It was during that time it was only 51% global population was using the internet access, but now by 2020 or 2023 you can see that this has been almost increasing to 66%. So this drastic increase in the internet users, it is approximated with respect to the global percentage from 2018 to 2023 as 6%. So here is a picture. This picture depicts how many number of internet users from 2018 to 2023 will be using. It is this particular graph, it is, if you observe, from 2018, in 2018 there were 3.9 billion of internet users, but as we move to 2020, it is 4.5 billions of internet users. But when it is moving forward around the year 2023, it will be increased to 5.3 billions of internet users. That is almost, it is an 6% of the internet users will grow from, which has been seen. There is a growth in the internet users. The second projection, which has been considered, is the devices and connections. So the internet, through the internet, how many global devices which will be used and what are the connections they are using. So the second projection says that globally, devices and connections which are connected to the internet growing 10 times faster than 1% of the population growth and 6% of the internet users. 6% increase growth in the internet users leads to 10% faster to connect the devices through the internet for the interactions, and which is very a faster phase compared to the population growth. And if you look at the per capita number of devices connected internet device through the internet, the devices connected on IP networks, it will be 3 times the global population by 2023. So this is an approximation. It has been approximated for the near future. In that, if it is considered approximately 3.6 network devices per capita, or by 2023, nearly 2.4 devices will be used by a person. This is from The 2018, if you go back and if you look at 2018, it is approximately 2.4 network devices per capita, but now it is going to be, in future, approximately it is going to double, and there will be 29.3 billion network devices by 2023, up from 18.4 billions in 2018. The major contribution to this devices and connections projection, it is due to the rapid research in the case of machine-to-machine connections. So these machine-to-machine connections will be half of the global connected devices and connections by 2023. It will be almost, you can see that it will be connected half of the global internet devices. These machine-to-machine connections, 2018, it was seen that during 2018, year 2018, only 33% of the machine-to-machine connections were there. There will be, in future, there will be 14.7 billion machine-to-machine connections by 2023. The major segments in case of devices and connections, if you look at it, is one is the machine to machine, the second one is the consumer segment. The three fourths of share of the total devices will be from the consumer segment. That is what the prediction by towards the year 2023. So globally, if it is considered the consumer segment share, total device connections will be 74%, with the business segment claiming the remaining 26%. So if it is the total number of devices, connectivity to the internet network, if it is considered, consumer segment contributes 74%, and the remaining segment, it is from the business segments. Another important vertical that has moved with the machine to machine connection, device connections, is the Internet of Things. Due to the rapid development or the rapid research growth in the Internet of Things, this Internet of Things is the another category of machine to machine, which will usually be used to connect home applications. So this Internet of Things, if you look at, by 2023, it will reach up to 45% of machine-to-machine share. And the another device connection vertical is the car applications. Since autonomous vehicles have come into the market, so by 2023, 30% of the internet users device connections will be towards the car applications. This is a forecast which has been made by for the years. If you look at the machine to machine, predicts that there are these machine to machine connections, including Internet of Things, which is depicted as follows. The almost 20%, the smart city connectivities, it is 26%, retail shops will be using 11%. So connected work in the work atmosphere, it will be up to 15%, it is going to increase. And car in the autonomous vehicles, it is going to increase 30%. Energy sector also is another contributor, which looks for machine to machine connection or Internet of Things. And health is the another health industry or health sector is also another vertical which looks for machine to machine connection by 2023. 90% 15%, manufacturing percent. Uh, Machine to machine connection or Internet of Things are the device and connectivities. The devices, we have seen how fast they are growing through the internet to access the information or to communicate internally. Parallelly, there is a growth in the mobile computing technology also. So this mobile computing technology research developments have advanced cell network advancements, which includes 2G, 3G, 4G, and 5G projections. If you look at these mobile mobility growth or the connectivity growth, the billions of devices connections through the 3G, 4G, 5G, and low power wide area networks have been consolidated here. When you look at the 5G networks, it is a wide band spectrum it is using. So this is a consolidated picture which represents how the advancements in 2G, 3G, 4G, and 5G led to the device connectivities. The graph depicts that 3G, third generation networks, earlier in around 2018, used to have the global market internet access with 55.3%, but by 2023 it will get declined to 29.0%. The 4G networks, 42%, 42.1%, it may go up to 46.0%. But when you go for the 5G technology, in 2018, almost it was in research stage, but when you look at by 2023, it may increase the utilization of the internet IP traffic by 10.6%. Another big growing vertical in this mobility growth is the low power wide area networks. In 2018, 2.5% was there, but it is growing very fastly towards 14.4%. So this is an network advancements along with the device connectivities increase rate. So if you look at almost the number of device connectivities which with the 3G towards 23 has been reduced, but the 4G has increased, 5G exponentially it is increasing. Similarly, low power wide area networks also it is increasing drastically. The another important, the third factor, which is the third projection, which has been analyzed or assessed in the digital transformation through this report, is the network performance and user experience. The 4G, it is when it is considered, it is mainly with the Wi-Fi, but this Wi-Fi now also it is continues to gain its momentum. So this particular graph depicts that during the Wi-Fi utilization and the drastic research developments in this Wi-Fi, uh, why the Wi-Fi is taking a momentum. In 2008 to 2009, there was Wi-Fi 802.11 standard, which was supporting 600 Mbps, megabits per second maximum, and we were able to transmit only medium resolution videos. But in 2009, the another vertical Wi-Fi modems have come up with 38 Mbps per channel and medium resolution videos. Around 2012, we can see that the modems with Wi-Fi standard 802.11 AZ, it is an high-speed modem. Uh, this is able to give an internet rate with an 3.6 gigabits per second maximum, and able to transmit a high resolution video. It is of wire complement. but later around 2019, still this Wi-Fi, because of the hotspot usage and then various hotspot usage, Wi-Fi usage in various sectors, various domains, the research still it is going in this 4G, fourth generation network systems, which has led to the another standard high speed low power modem. It is Wi-Fi 802.11ax, able to transmit 10 gigabits per second maximum, and usually this standard it is used to support for IoT, dense IoT deployments. So this is the vast majority of 1 giga developments will be due to the modems development and even the fiber communications and immerse videos, then virtual reality, high dynamic range, then high frame rate. These are the sampling rate has increase in the sampling rate to 8K. So these are the various aspects which contributed for the Wi-Fi to take a continuous momentum in the research field. And this Wi-Fi momentum still now it is used for virtualization, internet sensing will be supported, security aspects it is supporting, and data analytics also it is supporting. Another accelerating factor it is the speed on traffic growth. Sim is another issue that has to be discussed, that has to be seen for the future 5G or existing 5G network. Still, it is in developmental stage. The significant demand when the high resolution videos needs to be transmitted through this internet networks. So the home appliances in future they'll demand uh, what is the data rate or the speed. If you look at the picture, the near term it has been divided into two slots, the near term as well as the future, especially it is towards the home appliances. So 16% of the ultra high definition cameras now, ultra high definition streamings, virtual reality streaming it is of 17%. Then self driving vehicles diagnosis it is for 20%. Cloud gaming it is utilized, and it is 1%. The wall TV 8K sampled at 8K wall TV is using 100%. And in future, if you look at the high definition virtual reality may take an major role in this speed acceleration. It is almost 167, and the main contributor in the home appliances it is ultra high definition virtual reality products are the uh, aspects will go for future uh, employments or future scope for research. The mobile speeds when we are considering the internet users now at in the present fifth generation or fourth generation, they are using it is of either smartphone or the tablet. The major contributors to the mobile speeds to assess it is the smartphone and the tablet. If this picture, if it is observed in 2018, it was almost all network types 44, 15, 13 Mbps was the speed rate. But along with tablets were of 21 megabits per second, smartphones using 15 megabits per second, but it is near approximation to 2023. It is 44 megabits per second in the case of all network types, 59 megabits per second where the smartphones will be using, and 60 mbps will be the speed rate by the tablets in future 2023. The price rate, the tiered pricing, if you consider for the mobile, top mobile user profiles says that 4% of the mobile users consume 50 gigabytes per month as the uh, rate at which the users will be using the mobile internet access. So in this particular graph, you can see that greater than 50 gigabytes, 4% of the people will be using. Greater than 20 gigabytes, 18% of the mobile population will be using. 10 gigabytes, greater than 36%. Greater than 5 gigabytes, 59. Greater than 2 gigabytes, 82% of the mobile population. And greater than 200 MB, 99, almost all the percentage of mobile users will be using this internet access. With the rapid developments in the mobile devices, their connectivities, then the internet users, then the network performance parameters. Parallelly, there is another field vertical which is growing as fast. It is the security aspects. When the security analysis has been made, DDO, this is another threat that the mobile attack, which is going to hit the mobile users. So in 2018, the number of attacks 7.9 millions attacks, whereas in future 2023 it is almost 15.4 millions of attacks will which are the threat towards these wireless networks. So this is another key major field in the 5G wireless communications, which any researcher can look for the security aspects to consider. The fourth aspect are the projection. It is the next generation applications, because there is an rapid development in the internet speed, internet networks from 2G to 5G. All these led to the next generation applications. The next are future generation applications, which includes artificial intelligence and machine learning, which creates new models for business and industries. This is another application, next generation application through 5G we can think of. Most of the music industries also, they may go for the next generation applications for the better sound tracking systems to design and develop. The another application in the healthcare industries. Here, artificial intelligence and deep learning concepts have to be contributed towards the healthcare industries in order to have good predictions. The next domain in the next generation or fifth generation applications is the predictive analytics. So that is from industrial IoT, that is contributing towards the industrial IoT solutions like sensor working, or what is the predictive in future after some time, what will be the prediction in the some monitoring physical parameter or physical atmospheric variations it may occur. These type of predictive analytics will be done in as another domain that can be focused in the fifth generation applications field. The next field is an automotive industry, which is If the performance benefits of the fifth generation, because we have seen that there is an uh, increase in the number of internet users, there is an increase in the speed, so which has led to the developments in the network systems also, which supports for these increased number of users data, the frequency near to 1 millisecond, connection density has been increased, giving signaling for IoT connectivity, spectrum efficiency. It has been increased. The traffic capacity almost it is 1 to 1 increase, driving network hyperdensification, which has led to the low power consumption with more efficiency processing. So, where will this 5G cause the most disruption? Disruption in the fields, various fields which have been depicted through this graph or this plot, which includes 70% automotive, 57% cloud services, 35% manufacturing, 26% of the research contributes towards the retail, same 26% logistics and transportation, 24% online gaming and video, near to 30%, 20% healthcare, 13% energy sectors, 11% financial services, 9% government sectors, 2% agriculture, and 2% other fields. So these are the major disruptions through the 5G technology. These research and developments in the fifth generation networks, internet networks or communication networks, has been empowered employees and teams. Increase which has been increased the demands in IT infrastructures. If the IT infrastructures employments when they are considered, it is drastically increasing from unified management across network storage and computing, starting with storage and computing of the data from 35%, 36, near to 36%. It is growing up to almost 60% in the increase overall business agility. And if the global wireless networking matrices are considered, the wireless networking matrices says that by 2023, from 2018 to 2023, if it is approximated, more mobile users from 5.1 billion users to 5.7 billions have been increased, which may get increased mobile connections for the number of devices where it will be connected through mobile internet will be from 2018 go up from 8.8 billion to towards the 13.1 billion. And if the speeds mobile speeds are considered, it, from 2018 13.2 megabits per second may go up to 43.9 megabits per second. So this is the mobile momentum metrics that we can think of for the research and development aspect. So impact of next generation wireless communication. With all these developments, what will be the impact that is going to be on the future, that is next generation wireless communications? So these are the this is the reference wherein I have taken a few reference points. And the explosive growth of IP traffic demand resulted in gradually approaching the system capacity of the operational cellular networks, because as the internet demand is increasing in terms of speed, the number of users, usage, everything, it is increasing the demand towards the system capacity, and the which in turn towards the cellular networks. The main focus towards the system capacity that is required to be considered is for fifth generation network system. When the system capacity improvements for the fifth generation devices to interact, the challenge is suited in 5G technologies under three proposals. One is increased spectral efficiency, relying on multiple antenna techniques and novel multiple access techniques offering more bits per second per hertz per node. How to transmit, that is the one issue that has to be thought in detail towards the 5G technology. And the larger transmission bandwidth relying on spectrum sharing and extension as the larger, because 5G networks are using wideband, which works on wideband concept spectrum concept. Most of the time when the one or two users are communicating or using the internet 5G networks, other spectrum will be free. So how these spectrums can be used effectively, that is another aspect or the technique which has been focused in 5G technology, that is larger transmission bandwidth relying on spectrum sharing and extension. The improved spectrum, what are the algorithms which we can think of to improve the spectrum reuse, relying on network densification, having more nodes per unit area. In the as I told you, the key technical directions in 5G networks that we need to think of, it is one is the uh, multiple antenna spectral efficiency, transmission bandwidth. The third one is the spectrum reuse. The spectrum efficiency, if it is considered, the Shannon capacity, the channel capacity has been defined by Shannon's theorem. Here, the total network capacity, which can be approximated through this particular equation, which already we are using in our research groups. Here, when you observe this particular equation, I and j are the indices of number of cells and number of channels respectively. Capital I and capital J are the number of maximum cells and maximum channels per network which can be accommodated. There are two subsets which contributes for the channel capacity to define. One is the wij and the next one is the rho g. One is for the bandwidth, and the second one, that is rho ij, it tells the signal to interference plus noise ratio respectively. When the 5G fifth generation networks are considered, the three vertical domains which are majorly uh, uh, thought towards the research, it is one is the spectral efficiency, the second one is the transmission bandwidth, the third one is the spectrum reuse. It is a consolidated picture which depicts this theoretical concepts. The transmission bandwidth, when it is considered, why the research has been focused towards this 5G so seriously in terms of transmission bandwidth, because when the second generation mobile networks are considered, which includes which is based on GSM technology, that time 200 kilohertz was the transmission bandwidth, but later it has been increased to 3G, in 3G to up to 5 megahertz. But when you look at this 4G, it has been increased to 20 megahertz. The number of antennas, as this capacity band transmission bandwidth capacity, it is getting increased, the number of antennas employed also it is getting increased. When you look at the second generation or third generation systems where we used to have only one antenna, but when you move towards the fourth generation networks, almost eight antennas we need to deploy, along with the increase in the density of base stations, and also which are to be deployed, and also to support the users. Despite of this gradual quantitative increase of bandwidth, the number of antennas, density of base stations, and users have also increased. All previous wireless networks have relied upon the cloud, and when we talk about the increase in bandwidth, or the number of antennas to increase, the density of base stations to increase, or the number of users to increase, all these concepts rely on one basic fundamental theory. It is the Nyquist sampling theorem. The way back when you go for the second generation or third generation or fourth generation, if you look at different deployments in different domains, all the cellular wireless cellular networks were based on Nyquist sampling, working with the basic principle of Nyquist sampling theorem. What this Nyquist sampling theorem says, whenever we are transmitting a band width limited signal over a transmission channel, it can be completely reconstructed when this band limited signal, when it is sampled at a rate of higher than twice the signal's highest frequency. When the signal is considered in time domain, so it's are in the frequency domain, always we need to go for the sampling of such signals, keeping focusing which is the highest frequency component that is present in the band limited signal, the sampling rate will be considered. So fs should be greater than to fb is the Nyquist sampling theorem so far we were using. uh, in the Nyquist, when the Nyquist sampling theorem has been adopted, it has been adopted in the JPEG 2000, MPEG movie, that which includes the audio, video, as well as the moving pictures. So whenever such a information has to be transmitted, transform coding used to be used, where the signal used to be transmitted with a sampling rate which is twice the basic band limited signal. And whenever it is sampled, we'll be getting a signal of length n. sorry, we are going to get when it is sampled, get the signal of length n, transform this signal having length n with the measurement coefficients k, which is very much lesser than n. And when after transforming, we will observe in the JPEG or JPEG 2000 MPEG, or in audiovisual codecs. Many codecs have come in the market for high definition videos to upload. uh, this transformation gives non-zero coefficients. Most of the time after applying the transformation, the entire information or the signals information will lead very few non-zero coefficients. So these non-zero coefficients preserve are represented as k. After transform coding, these k coefficients will be preserved and their locations also will be preserved. But when you move towards the development in the field of the fifth generation network systems, or the emerging 5G solutions, which requires at least 100 megahertz bandwidth, where this 5G has to support hundreds of antennas, ultra densely deployed base stations for the support of massive users. So this is a basic problem which has led to the compressive sensing. But actually, when you go for the transform coding or the basic Nyquist sampling theorem and transform coding, now also in H.264 or HEVC also you can see that there is an high definition video transmission which is supporting on 5, which will support for 5G networks. So before the compressive sensing I start, so what this transformation coding, or how the Nyquist sampling which will be processed practically in order to support these theoretical statements has been illustrated here with a simple block diagram. So the compression, when we talk, because most of the antennas, more as you increase more the bandwidth, more the number of base stations, more the number of users, the digital transformation data which is going to increase enormously. If this data needs to be transmitted, huge bandwidth, huge infrastructure, high power, all these are required to have in order to tackle these issues in the coding technology. It is a H.264 audio visual codecs have been designed with the following uh, techniques, where the video or the image will be subjected to many sub processors in order to have a low bit rate per channel to transmit over a channel or the wireless networks. If you look at any frame, in order to have the redundancy removal, the each frame will be compared with the, in case of video, will be compared with the reference frames. And this uh, reference frames, the deviation or the error signal used to be considered for the transmission. But before this error signal from the current frame and the next frame in terms of pixels matching, when it is derived, that will be subjected to the transformation. It may be the DCT, or it may be the discrete wavelet transform, discrete cosine transform, or integer cosine transforms we will be adopting. And after these transformations, again the signal will be compressing through the quantization techniques. There are non-uniform quantization techniques, plenty of quantization techniques you can see. So any of these quantization techniques we may make use in order to further compress the signal to support for the limited bandwidth channels. And that band limited signal or the compressed signal will be uh, reordering, and then we'll be encoding through the entropy encoding techniques. There are many arithmetic context adaptive variable length coding, and then CAVLC. Many algorithms you can make use and you can transmit. But during the transmission, the network abstraction layer will be used, because that will be considered as a channel for the audio or video to transmit. But this, when it has a limited capacities to support these many sub process, will be considering when we go for an any audio or video to transmit. After transmission, how do this will be the reconstructed at the decoder side. There will be an entropy decoder, then reorder, that is zigzag scanning, all those things many are there. So that will be done, and inverse quantization will be done, inverse transformation will be done, that will be added with the reference frame. So that, and after adding, the original picture will be depicted back, which will be further supplied or subjected to and filter. It will be a deblocking filter. If you consider this compression technology, that is where the Nyquist sampling theorem we are using. Here, if you observe the reconstructed image or reconstructed uh, video, gives almost an good efficiency. So what happens when the Nyquist sampling, same Nyquist sampling rate, when it is used for the fifth generation networks, or this has a few challenges. Those challenges are listed here. The Nyquist sampling rate changes indicate that applying Nyquist sampling theorem to fifth generation techniques reminiscent of the previous second generation, third generation, fourth generation solutions may result in presented challenges. What are those? Prohibitively large overloads, because fifth generation huge in data, which leads to when a Nyquist sampling rate it is applied, it gives the large overloads, which increases the complexity of the system, as well as it increases the cost as well as the power consumption of the systems which we are going to deploy to for the fifth generation networks to support. Given the large bandwidth of the next generation systems and the proportionally high Nyquist frequency, we arrive at an excessive number of resolvable multipath components, even though only a small fraction of them is not negligible. So this led to the another important vertical in the technical field towards the research is the compressive sensing. When you go for this compressive sensing, because in the day before session or yesterday's sessions, many speakers they have in detail discussed about this compressive sensing. The compressive sensing offers what this compressive sensing means. This compressive sensing offers a sub Nyquist sampling approach. Instead of having the samples double the maximum frequency of the basic modulating signal or base band limited signal, we will be going for another thinking. It is what means go for a sub Nyquist sampling. What this sub Nyquist sampling means, always the samples we are going to consider lesser than the actual sampling, which also will support for the reconstruction effectively. In the compressive sensing, one important key term we'll be using, it is the sparsity. This sparsity is a common term in compressed sensing. It is in the mathematical sense, because when we go for compressive sensing, one is apply the Nyquist sampling theorem, go for more number of samples, increase the data rate, transmit over a transmission bandwidth, go for more complexity, high power consumption, high risk in hardware deployments. The another way how to tackle these issues, it is, can we go for this compressive sensing? This compressive sensing, as I told you, in this technique, the undersampling will be done. In this undersampling, what is this undersampling? Is to understand, first one term we have to understand is the sparsity. This sparsity is a common term in compressed sensing. In the mathematical sense, sparse collection of data has a small number of non-zero values. To put it simply, most values are zero and only a few contain meaningful data. So this is what the main technique that we are going to use in the compressive sensing. Rather than using all the samples of all the signals, very useful samples you can take and you can transmit. This compressive sensing, in simple, when we are talking, a sample with rate lower than Fs, that is the Nyquist rate. Fs is your Nyquist rate. You reduce the sampling rate, which is lesser than Fs. The question arises, through this compressive sensing, can we able to recover the data? Yes, we can recover the data perfectly, and we can reconstruct the uh, transmitted information completely through this compressive sensing. In simple, if you are going for a comparison between the Nyquist sampling and compressive sensing, sampling frequency, it should be greater than or equal to twice the baseband frequency, maximum baseband frequency or band limited frequency. But in compressive sensing, the sampling will be lesser than 2 FB. Recovery, it will be done through low pass filter, and in compressive, that is through the Nyquist sampling. But when we go for compressive sensing, it is done through convex optimization. What is a basic mathematics which is behind this compressive sensing? So let me brief in detail, because in brief, because yesterday's session, one of my colleague, he has explained in detail this compressive sensing. Imagine we have, what is a basic mathematics means, imagine we have a signal x. This signal x in time domain will be representing with a length of n. In a perfect world, we would simply take n measurements. If we need to reconstruct in real time, a real world, what we'll be doing, n measurements we'll be taking of length n signal, and call it a day. So, however, today we can take only k measurements instead of, because we know that if we go for k n measurements from an signal x having a length n, the problem which may raise, it is towards the complexities, various complexities. So therefore, we can go for the k measurements, where these k measurements of signal length n, if as of signal x, when you are comparing with the signal length n, it is the number of measurements what we are going to make use will be very small compared to the signal length. We use a vector y to represent our k measurements. So because ultimately, whether you go for the less number of samples or more number of samples, the ultimate final goal is to reconstruct these signals back. So during the transmission, a vector y will be transmitted, which will be represented with only k measurements. What's important to note is that one measurement does not necessarily correspond to a single input value. The in depth meaning of this in a while we explaining. In order to get y, what will be the mathematics which we are going to make use? We use a matrix A. Simply, the output vector will be representing in terms of the input signal, and the matrix A, it is represented as y as equal to a into x. What this A matrix is? It is also a vector. In compressive sensing technology, A represents the sensing matrix, which allows us to get from x to y via random measurements, transformations, or combination of both. There may be a random measurement or there may be a transformation. We'll be adopting through this. We'll be adopting on this sensing matrix. To summarize, we have the following: X is a signal having length n, which is in terms of the vector representation having a dimension n cross n, n cross 1. Y is another matrix we are deriving from the k measurements of n signals, n length signal, which will also be equal to k into 1 cross k cross 1 vector. And when we go for the sensing matrix will be k cross n sensing matrix. How we get from input to output is a question that will arise. Suppose if we go for uh, x of length n, which is equal to 8, has a random values. We have to, having this length of 8 signal, we have to only keep only 3 components from this length x, three signal components from length n, or n is equal to 8. Let us say in this particular slide, you may be observing there is an A matrix, then this is what the X is, and this is what the Y is. Let us say the first, second, and the fifth components of this X having length n equal to 8 is of important information that has to be transmitted during that time. How do we construct the sensing matrix? The sensing matrix will be always m cross n, and whichever the component that is required, that is going to be made in the unitary matrix as 1, and corresponding unitary matrix with an unit value of 1, and other components in the sensing matrix will be made 0, so that the resultant matrix will be the compressed matrix. This compressed matrix will be having the only region of interest components. In the above figure, we are clearly keeping 3 samples of our original values and throwing away all other 5. If x is spare signal, mean to say that if you are in the previous example, if you observe, x is not space. Every coefficient is a non-zero coefficient in x. Suppose the second case, if you are considering in compressive sensing, if your input signal is of a what is that spare signal, so mean to say that very few values of the signal are existing in this signal, then such a sensing matrix if we adopt, and we may lose some of the important informations which are existing in the sparse signal. To overcome these problems, we because we will be losing ones, we might lose the ones we need. Important coefficients we may miss in this signal. This is because we don't know the location of the values, useful values beforehand. This approach to overcome, we have a different approach. In this, we have used in the compressive sensing the different approach. In the compressive sensing, the other approach is that have a sensing matrix which is not non-zero. which is derivative, like when we go for transformation in the discrete cosine transformation or inverse cosine transformation or integer cosine transformations in with the Nyquist sampling, there we'll be deriving an transposed matrix which is of unitary matrix, and that will be having a property when at the reconstruction it will be an orthonormal basis function. The same technique it has been adopted here. We need a different approach so we don't lose our non-zero values. Fortunately for us, if we use Gaussian, here what is the technique that we are going to adopt to overcome those spare signal losing coefficients information? We'll be adopting Gaussian random variables. So, to define the sensing matrix, whenever the Gaussian random variable sensing matrix is used, there won't be any threat of losing a data even though the signal is very sparse. This phenomenon inspires us to sample the resultant sparse channel impulse response as well as other signals under the framework of compressive sensing, thus offering us opportunities to tackle the above mentioned challenges. So, since Gaussian variable random variables we are using, even though signal is of sparse and very few limited components in an sparse signal, effectively, efficiently, these signals can be transmitted, and also the compressive sensing mm, can be efficiently will be very efficient. If you compare the traditional data sampling and the and compression with the compressive sensing, these are the two figures which depicts what the traditional data sampling is and what is the compressive sensing is. When you go for the traditional data sampling, here we'll be going for the sampling which is greater than which satisfies the Nyquist sampling theorem. After the Nyquist sampling theorem applied onto the signal, it will be subjected to the compression. Various compression algorithms will be applying where through these various compression algorithms, the redundancies will be removed, highly correlated signal will be made very sparse signal, and such a sparse signal will be transmitted over a transmission channel. But when you go for the compressive sampling, here the signal will be considered. During the sampling itself, the compression will be taken care and the measurement vector will be generated. So here there won't be any compressive other algorithms which we are going to add as extra, which reduces the hardware complexity, which reduces the computational power, which reduces the hardware infrastructure, which reduces the power consumption. Then cost of the hardware will reduce. These are and the speed of the processing will increase. These have been the motivational factors. This compressive sensing is the motivational factors towards the fifth generation networks. So example of compressive sensing. Okay, this is another approach we are using. Sorry, I've gone back. Okay, how this compressive sampling and decompression framework will be done through the compressive sensing. A framework has been illustrated here. We'll be taking an sensing matrix, which is termed to be an measurement matrix having a dimension of m cross n, will get multiplied with a signal of interest, and through that we'll be generating a measurement vector. This measurement vector is this signal of interest will be considered from an actual signal. How it has been derived means sparse vector will get multiplied with a representation matrix. Usually they will be based on the orthonormal basis functions. And at the reconstruction, please, you will be taking the measurement vector, and this measurement vector you are generating through the sparse vector, multiplying that sparse vector with the reconstruction matrix of m cross n. So this is how this picture, which depicts the framework, how an orthonormal basis function, which will be initially multiplied with convolving with the actual signal, thereby region of only sparse signal will be considered for the transmission, and how this compressive sensing, when it will be used and how it will be used, for which you must know the two things. This compressive sensing you can apply when the signal is compressible, and which is of sparse in nature. Okay. And how this will be done, how to design the sampling matrix, how to decide the sampling rate, that is based on how the signal, whether it is very sparse or less sparse or medium sparse, based on this, the sampling rate and the sampling matrix will be decided. So the sampling matrix, when we consider, it should have the low coherence. And after the compressive sensing, the signals will be uh, after the compressive sensing signal is getting transmitted, the spare signal will get transmitted and it will be reconstructed at the receiver side or the decoder side. How this reconstruction will be done, there are many algorithms. I am not going in detail with these reconstruction algorithms. Many reconstruction algorithms are defined on compressive sensing. Still these are, algorithms are in research and developmental stage. These research algorithms, if you look at, which have been elaborated in this particular block diagram. So at the transmission side, this is what the compressive sensing reconstruction algorithms. At the there are majorly three reconstruction algorithms in compressive sensing. We'll be using, one is the convex reduction, the second one is the greedy iterative algorithm, and the third one is the Bregman iterative algorithm. So these are the reconstruction algorithms which we can make use in order to reconstruct the sparse signal having limited number of samples in an efficient and effective way. The key directions, as we discussed, it is in the higher spectral efficiency. So in the towards the fifth generation networks, when we are considering, initially massive MIMO schemes were there. Here reduced overhead required channel estimation. This is the one fifth generation topic that we can think of. It is towards the high spectral efficiency, that is the massive MIMO schemes. In this massive MIMO schemes, in the fifth generation, this compressive sensing theory has been employed to reduce the overhead required for channel estimation. This is one key research focus that we can focus MIMO technology. The second factor towards the compressive sensing is the massive spatial modulation, that is SM-MIMO schemes. Here, every user will have different frequencies, different antennas, and different RF frequencies. The using compressive sensing in SM-MIMO, the challenging task is to estimate the massive SM-MIMO, how since only a fraction of the antennas are active in each time slot. So this is an spatial modulation MIMO scheme where at the same time when all the networks are being observed or users are being observed in SM MIMO, every user, since will have different RF frequency, they'll be using very sparsely the channel. So using compressive sensing, how these sparse channel effective efficient utilization can be made, it is an another fifth generation research aspect that we can focus on. The third or the next research focus is on sparse code words in orthogonal multiple access systems where the compressive sensing through different code books when it is applied, how effectively the antenna or the base station deployments can be increased that we can think of, and how the multiplexing we can go for it. The larger bandwidth, when we are talking towards the fifth generation, the larger transmission bandwidth, it is in three different domains we can think of. One is in the cognitive radio, that is where wireless wideband spectrums are supporting. Ultra wideband transmission is another transmission bandwidth. More utilization transmission bandwidth, compressive sensing research topic. Millimeter wave communications is another compressive sensing research topic. Better spectrum reuse, how using this compressive sensing, how effectively the base stations identification can be done, massive random access can be done, traffic estimation and prediction of energy in an efficient dense networks we can think through this compressive sensing. What are the applications of these compressive sensings? Compressive sensings in the world of multimedia communication, that is with the compressive sensing, introduction of compressive sensing cameras. So this is one compressive imaging in that CS cameras, that is compressive sensing in cameras. Now, if you look at the market, in the market, the compressive sensing cameras are available, and these compressive sensing cameras have the lot of advantages compared to the high definition cameras. These compressive sensing cameras reduces the number of measurements, hence power consumption, computational complexity, and storage space without sacrificing the spatial resolution. These are the advantages, are the main features of these cameras which are designed with compressive sensing. If the medical imaging is considered where high redundance information will be available, like MRI, there the compressive sensing can be pursued for medical imaging in case of the magnetic resonance imaging. MR images like angiograms have sparsity properties in domains such as Fourier or wavelet basis. So seismographic imaging also can be thought in this by applying this seismic data is usually high dimensional, incomplete, and very large. So in order to support such a seismic imaging, the compressive sensing can be adopted, and through this compressive sensing, the spare sampling can be done, and thereby this high dimensional incomplete very large image data sizes can be effectively transmitted and uh, reconstructed. The another application of compressive sensing is in the biological applications, so such as compressive radar, analog to information converters. These are the biological applications where this compressive sensing can be adopted for efficient and inexpensive sensing in biological applications. Thus, compressive sensing in communications and networks also it is supporting. So, very in brief, I'll be consolidating these communications and networks in which fields this compressive sensing it is going to be adopted. The channel estimation, that is sparse channel estimation, where the compressive through compressive sensing, the sparse channel estimation can be effectively efficiently done. Uh, that is one of the research scope. Spectrum sensing in cognitive radio networks through this compressive sensing, then ultra wideband networks, wireless sensor networks, erasure coding, then network management, multimedia coding, and communication. These are the fields Not only these fields, still more few fields wherein we can this theory of the compressive sensing, it is in developmental stage, can be adopted to have more research towards the communications and networks. One of the application, if we consider, is the image compression. This image compression using compressive sensing, how it has been done, it is illustrated through this simple flow chart, where we'll be taking this flow chart consists of encoder and decoder parts. Encoder will have the original image that we'll be normalizing, applying discrete wavelet transforms, generating the measurement vectors. After that, quantization will be done, then packaging will be done, then entropy coding, encoding, and thereby the channel, over the channel, it will be transmitted. At the decoder side, in order to get back the image, we'll be going for entropy decoding, unpacket and dequantization, bit loss, if yes, regrouping measurement matrix, if no, minimization algorithms to reconstruct effectively. This is a measurement matrix which will be telling what is the compressive sensed reconstruction image characteristic is, so that L1 minimization algorithm can be adopted, inverse discrete wavelet transform, and then denormalization to reconstruct. This is a simple flow diagram that can be thought, because when you go for the compressive sensing technique adaptation at various levels of encoder and decoder, still the compressive sensing technology is in the developmental stage, not fully full-fledged. Normalization is able to give discrete wavelets and so on. At all the stages, the research can be thought. This compressive sensing network in communications and networks, it also supports for compressive sensing based localization, video scrambling, traffic monitoring, then anomaly detection, network data mining, distributed compression in wireless sensor networks, and network security. So these are the various research fields which we can think of in the fifth generation networks through the compressive sensing. Finally, let me conclude my conclusion presentation. This compressive sensing theory has provided a Nyquist sampling approach to efficiently tackle the above mentioned challenges for these key 5G techniques. Investigated the exploration of sparsity in key 5G techniques from three technical directions have been already discussed. It gives a open problem for future research and future research directions for the perspective of compressive theory in fifth generation. Also, we theoretical research and how this theoretical research can be converted into the practical approach in future. CS algorithms exhibiting reduced complexity and increased reliability, as well as compatibility with current systems and hardware platforms, will be the potential future research topics which we can think in this compressive sensing towards the 5G technology. Play a critical role in designing future wireless. This compressive sensing, finally, to conclude, plays a critical role in designing the future critical networks. Hence, our hope is that our valid colleagues might like to join this community effort in finally to conclude. So these are the references which I have considered to prepare my presentation slides. So
Thank you, ma'am. Thank you for providing an excellent presentation with respect to CS compressive sensing network theory. And we learned about compressive sensing algorithm exhibiting reduced complexity and increased reliability. And also, with respect to this, examples related to compressive sensing networks and all. Thank you very much, ma'am. If any queries are there, participants can ask in a chat box. In chat box. Any queries are there? There are no queries, ma'am. They have given the feedback like good presentation, excellent presentation, and all. And some international uh, participant is also available from Nigeria.
If yes, madam.
Thank you very much.
If
Thank
no
you, one
questions,
and all. Yeah, if any
I
queries are there, ma'am's mail ID will be provided.
yeah.
And
Thank you, madam. And one apology because of network issues, I was not able to connect in time, but later I've joined, for which I'm extremely sorry from my side.
thank you, ma'am.
Thank you.
And thank you for attending this morning session. In afternoon session, we have our keynote speaker, Dr. Keshamurthy, Professor and Controller of Examination, Sri Venkateshwara College of Engineering, Bengaluru. Sir will be delivering the session on MIMO, OFDM, Systems and Channel Estimation. Please don't miss the session. We'll join back at 1:30. Thank you, one and all.
Thank you, madam. I would like to thank on my behalf all the participants as well as my coordinating team, all coordinators for the organization. Thank you.